So for this particular module, module 7, I would like all of you to remember what does your protic compounds are, what are your nucleophilic and electrophilic compounds, and also your general chemistry, which where you have learned about the energy diagrams and so on and so forth. So what you see in front of you is the first half of the chapter 7. Chapter 6 assignment is due this coming Saturday, but it is this chapter 7 which is very important. And after your lecture, you should definitely read the corresponding parts in the book and also try to make your own notes. So this is an energy diagram of a chemical reaction. What we see here on the y-axis is the energy. What we see here on the x-axis is time and coordinate of that time or progress of the reaction. So as the time passes from 0 to 20 minutes, for example, what is happening here? But when we talk about chemical reactions, they are occurring in nanoseconds. So their time limit is very, very, very short. So from the reactants, we make our products. And whenever from reactants you make products, we are assuming those products are going to be the stable structures. And so from now on, we will not only just look at the stability, we will also have to look at the rate. So if you have two pathways, A going to B from one pathway and A going to B from the other pathway, which of these will be faster? And this is what your activation energy describes us. This is the energy which is needed for the reactants to go over or cross over so that it can make the newer products. And so E activation describes the rate of the reaction, while the stability is defined by the Gibbs free energy change. Now during this, we will also look at delta H. And delta H is something that your Gibbs energy is dependent upon. So we will not be looking at much of your physical chemistry part. We will just overlook it and I will try to explain to you what are the important parts. So our delta H tells us the final destination minus the initial point. So that could be from products to reactants or from reactants to products. So if you have to tell me the delta H from the reactants to the products, you know your initial are the reactants energy and your final will be the energy of the products. Another thing that your rate or the kinetics, the E activation is dependent upon is temperature. Usually by external factors like catalyst or increasing temperatures. By these factors, we can change the E activation of our reaction. Okay. And so these are the things that you need to remember from your general chemistry class. We will also be looking at the exothermic or exergonic or endothermic or endergonic kind of reactions. Whenever you will have an endothermic reaction, for an endothermic reaction, your transition state will resemble more of your products. When you have an early transition state, it will resemble more of your reactant. So in an exothermic state, your transition state will be similar to the reactant. In the endothermic state, your structure will be very similar to that of your product. So knowing your E activations, your products, where the products lie, where the reactants lie, where is the transition states, and what are the intermediates. So that's the next thing that we have to look at. Oops. Intermediates are some things that we can isolate, and you don't have to understand these graphs right away, but I just want to explain some parts of it to you. So if you look in this particular reaction coordinates energy diagram, how many E activations do you see? We only see one. What is right here is a transition state. The reactants are transitioning to products. How much energy is required between the reactants and the transition state is the activation energy. So that is your rate determining step. In this reaction coordinate, we only have one step for the chemical reaction. However, for this energy diagram, I have two activation energies. 1, 2. How many transition states will I have? I will have a transition state 1. I have a transition state 2 here. So what is in between right here? This is the intermediate. This is not our product. This is a material in between our reactants and products. Just like your reactants and products are materials that can be separated out, isolated out, exactly same way your intermediate can be separated or isolated out. Transition states, on the other hand, cannot be separated out. Because you see two activation energies, we know this is a two-step reaction. Any questions so far? Now remember, the rate of reaction is judged or determined by the activation energy. For the same products, between these two, visibly also, which is bigger, the blue one or the pink one? Visibly also, we know that the E activation for this step is more. So this step will need more E activation. It will take more time to occur. And so overall, the rate determining step, or RDS, is the one which takes the most time or needs most energy. So the overall rate of the chemical reaction will be determined by the rate determining step, or the step that takes the longest time, or the step that takes more activation energy. On the other hand, the stability of the products is decided by Gibbs free energy. Now, Gibbs free energy also decides the enthalpy, the entropy, okay, the delta S. Now, let's very quickly look at what is the factors that determined our delta G, or the Gibbs free energy. So these may be some things that you will be seeing very soon on your drill manual tests also. Delta G, delta H, or enthalpy decides or is decided from bond dissociation energies. Now, you don't have to memorize any of these energy values, but what is it that you need to know? So, for example, if you have a reaction going from this to this. So overall, what has happened? The CO bond broke and the CBr bond formed. So you will see in that table, in a dissociation table, what is the energy required to make this bond and break this bond. This is your initial, this is your final. So delta H is always calculated from final energy minus the initial energy. The second factor that your Gibbs free energy or Gibbs energy, as we just simply call it, is dependent upon entropy. Entropy is nothing but the amount of randomness or disorder that can be present. So if we have a linear structure, let's say I have a linear structure, and then somehow it becomes a ring kind of a structure. Which side will have more S? Which side will have more randomness or disorder? This part with the linear chain will have more entropy or more S. This one where you have actually confined your linear structure will have less S. Okay? So what do you need in your reaction? If you look at a reaction like this, you have a linear chain and then you make a cyclic ring. Again, you have decreased your entropy. So overall, less S minus more S will give you a negative delta S. Yeah. And let's say that you have a long structure A, B, C. So all of this is just one structure. And then by somehow you can dissociate all of them. What are you doing now? In your product section, you now have more S. And in your starting, you had less S. All of them were confined. There was less randomness or disorder. So overall, this reaction will have a positive delta S. Okay. Now, another important factor that we will need to know, and all of this I'm concising because all of you are required to do that assignment where you have to read in more details about the rates and the reaction diagrams and the energy diagrams and so on, is the Hammond postulates. And we just looked at the factor that the transition state will be closer to which part? Transition state will be closer to products when during endo or endergonic reactions. And so during that, the energy of your reactants is less while the energy of your products is more. And even though most of the times these kinds of reactions are not possible, remember in chemistry, we always want to get more stability in your products. This is deactivation. And this is delta G. Delta G is positive. Usually these reactions are not possible. we have to put extra effort. For example, some extra energy or some catalyst for this kind of systems to work. So we say these are non-spontaneous kind of reactions, where the reaction favors the reactants. Yeah. On the other hand, your transition state will be closer to reactants during exothermic or exergonic kind of reactions. Of course, the reactants are at a higher energy, products are at a lower energy. So the transition state resembles the reactants more. This part will be very important to us as we study our further mechanisms. Okay. Another important part of this module will be the factor that you need to know about rates. So remember, Gibbs free energy tells us about stability. This is telling us about stability. The second factor that we need to know from this module is the rate. And who tells us about the rate? The activation energy. Now there are several mathematical relationships that are there, but for us, we will only focus on this particular equation, where it's clearly stated that the rate of the reaction is dependent upon the rate constant. So this is a small k, rate constant for that reaction, and the concentration of reactant or reactants. And usually for the rate, in the superscript, we have what is known as the order of reaction. Order of the reaction is the degree to which concentration of reactants affect the rate. Let's look at an example. So let's look at a generic example where A plus B gives us C plus D. Now the order of the reaction is different from the stoichiometry of the reaction. Is there anyone who does not understand the difference between the stoichiometry of the reaction and the order of the reaction? Anyone? Ariel, do you understand what is a stoichiometry and what is a order? They are two different things. Ariel, do you understand that? Okay. How about Salome? Salome, can you figure out if the order of reaction and the stoichiometry of this reaction is different?
Yes, ma'am.
Okay, can you tell me what is the stoichiometry of A in this reaction? So whenever we have a chemical reaction, we always try to balance it, right? With some numbers, with whole numbers, right, Salome? And
yes, ma'am.
so what is the number that I have for A here?
1.
1, very good, Salome. Thank you. And so the numbers with which we balance out the compounds, they are the stoichiometry. The order of the reaction is something that we have to find out experimentally. This is done experimentally. This can be found out by just balancing the chemical equation. So let's say that for this particular example, it was found that the rate is small k, and then concentration of the reactants, both the reactants. And according to the experiment, we see that the reaction is second order with respect to A and first order with respect to B. So please pay attention, the stoichiometries are different than your order of the reaction. So what will happen if the concentration of A is doubled? Okay, so this is our original rate. I'm going to label it as rate at 0. I'm not changing anything. This is what the experiment told us. When I'm changing my concentration now, my rate is now new. Let me write it, rate prime. The rate constant will be same. The concentration of the B and the order of B will be same. What will be different? Instead of writing A, I should write what? Anyone? So because I'm doubling it, what should be the concentration of this compound be? What should I write here? Michaela, do you want to help with this? Okay. This is it. So I'm just doubling the A. What is the next step? How has the rate been affected? So let me write rate prime equals, oh, this is not this, is equal to A square. And out of this, I'm going to write the 2 outside. What is the 2 square mean? 2 raised to power 2 is 4. So I'm going to write 4 outside. My B is exactly the same with 1. I will divide all of this with my initial rate. Rate 0 equals K A square and B 1. And so what do I see? I can cancel out these varieties. What is left with? What has the effect of doubling my concentration of A do to my rate? It will make it 4 times. It will increase the rate 4 times when I will double my concentration. Any questions so far? Okay. So before we move forward, I just want to remind you that for an energy diagram, remember, if I have a setup like this, and if I have from the same reactants, I can make 2 different products from the same reactants. My energy diagram can help me figure out whether I will get kinetic products or whether I will get my thermodynamic products. So knowing what is kinetic, what is thermodynamic is very important. Kinetic means how fast these products were formed. Thermodynamics means how stable the structures of these products or how stable they are electronically. Products that have been formed quickly or very fast, they may or may not be having very stable structures. Are y'all with me? So from the same reactants, using different conditions, we can generate kinetic products, we can generate thermodynamic products. Definitely thermodynamic products are more stable. But sometimes, just sometimes, you also have to know how fast your products can form. I want all of you to go ahead and draw this carefully in your notebooks. So these are the three things that I have. All of you should be able to figure out the number of steps in this chemical reaction, which is the rate determining step, and how many intermediates do I have, how many transition states will I have here. So go ahead and draw this out and let's talk about this. So all of you have this structure?
Yes.
Okay, thank you. I'm going to launch a poll now. How many transition states and how many intermediates are here respectively? So you have to tell me the number of transition states first and then the number of intermediates in this particular example, okay? Now looking at the energy diagram, these are the things that you must always understand. Besides the fact that are you forming stable, the thermodynamic product or a kinetic product? Remember, kinetic products form faster, but they may not be stable. Thermodynamics products will always be a stable structure. What does stability means? Low energy. Okay? But our question from this graph is how many intermediates and how many transition states are in this structure. I'll give you 15 more seconds and then I'll end the poll. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, And I'm very, very pleased. Most of you, 60% of our class, has chosen the right thing. Remember, each of these humps tell you about a transition state. So 1, 2, 3. 3 transition states. Very good. And between a reactant and products, how many intermediates do we see? We say intermediate 1 here and the intermediate 2 right here. So very good. How many number of steps does this reaction has? 1, 2, 3. So looking at this diagram, this is a energy diagram of a 3-step chemical reaction. The next question is it thermodynamic or is it kinetic? Because the energy of the reactants is more and the energy of the products is less. This is a thermodynamic kind of a product which has more stability towards the products. And the last question, which is very important for all of you to recognize, is which is the rate determining step? Anyone, can you take a guess? Which is the rate determining step? So you can mention going from this intermediate or going from this reactant. You can mention that.
It's step 2 from intermediate 1 to intermediate 2.
Exactly. How do we determine our rate determining step? And thank you very much, Nelson. The one which has the maximum E activation. If you look at all of these, from this starting point, the next hump is right here. So this is our first E activation energy. From this intermediate, I have this activation energy. It has to cross all over this energy to come to the next step. The last step also requires some E activation energy. But among all of these 3, this will take most time. More E activation is needed, more time will be needed. And so from this step to this step, or the second step, as we can say, will be the rate determining step. So very good. So knowing all of this information basically will help us to cover the chapter 7. So that is probably in your chapter 6 of the 3rd edition of Klein. But what we are going to look at now will be in chapter 7, where we will be covering the basics of all the reactions and mechanisms. So we will be looking at ionic reactions. Remember, what are ionic reactions? They are movement of electron pairs. And we have already looked at one of the reaction mechanistic steps. So ionic reactions have basically 4 kind of mechanistic steps that you need to know about. Sometimes you might get a question towards the end of the course to devise your own mechanism also. So the first ionic reaction mechanistic step that all of us have already looked at are the acid-base reactions, which involves protonation. So that is the first part. How do you know protonation? You need to remember the curved arrows. Curved arrows always go from electron rich to electron poor in a curved manner. So if you have a reaction like this, which is our regular acid-base kind of reaction, among both of these, where is your electron rich part?
OH.
Yes, the lone pairs of oxygen, they will become your basic site, and the hydrogen of the Br, of the electronegative element, will become your acidic site. And so following, the protonation occurs and a bond breaks. So this particular step is your protonation step. What happens in the process is a leaving group also occurs, and we will see leaving groups in more details. So in acid-base reactions, you have a protonation where a proton is abstracted or kidnapped, and a deprotonation step also. So a deprotonation will occur when the hydrogen is removed. Most of the times we will see this. Let's say we have a system like this. A base will appear. Where does this base appear from? It could be anywhere. It can be within the system. It could be introduced from outside the system. So it does not matter as long as you know a base with a negative charge. So B with a negative charge is the short form for base. So this base will abstract out an acidic hydrogen. This is my basic site. One of these hydrogens connected to an electronegative positive hydrogen will become my acidic site. So I'm doing a deprotonation. This part, in this part, protonation, deprotonation of this molecule. And now we are doing another deprotonation. You will see very common deprotonations occurring. When this hydrogen leaves, it breaks the bond with the atom it was with, and now we have a HP. What is this? Most of the reactions you will not have to explain what it is. Just remember what is electron rich and what is electron poor. Electron rich will be your nucleophile, and this is on our slide 24, I think, or 20. So in our module 3, we had looked at basicity. When we looked at basicity, we remember that base is electron rich. Okay, electron rich, and it would prefer to have a negative charge, some excess electrons. That is what the negative charge is. That's what the electron rich species would like. On contrary, nucleophile and basic compounds, they're very similar. Both need to be electron rich. So many of the nucleophiles that we see, for example, are hydroxides or methoxides, all of these can be both nucleophile and base. But how do we differentiate between a nucleophile and a base? This comes because base also needs to be a bulky material. Nucleophilicity is kinetic based. How fast the bunch of electrons can move. Basicity, on the other hand, is not for movement, it is for polarization. Okay? So both of our basic and nucleophilic materials want to be strong electron donors. Who are strong electron donors? all the negative charges are strong electron donors. Who are poor electron donors? Weak nucleophile, weak bases. Neutral molecules. If you look at ammonia, if you look at all of these examples also, all of them are neutral molecules. They can give lone pairs, but not as strong as these negative charges. These are also neutral nucleophiles. These cannot behave as base. So between nucleophilic basic parts, you have to remember these hydrides. Bulk and polarizability affect basicity. Nucleophiles just want a very big atom, okay, but not bulky atom. So if you compare SH, okay, and if you compare OH, S is a bigger atom. It will only behave as a nucleophile. OH can behave as both a nucleophile and base. So remember, C negative is the strongest base, followed by N negative, followed by O negative. Okay? And we will see some of the C negative as being very strong nucleophiles also. So knowing your differences between nucleophilicity and basicity will definitely help us when we go to E1 and E2 kind of mechanisms. But in general, just remember, every time you will have a negatively charged molecule, you will have strong electron donors. What about these guys? These are neutral. So we know that they are not as strong electron donors. But what about this? And what about this? These are resonance stabilized. Their electrons are not available for attack. Why? Their electrons are busy spreading out, making the molecule stable. If something is stable, it is not going to attack that well. And so bulk and resonance stabilization interferes with the electron donating abilities. Larger atoms are polarizable, like sulfur atom, which increases nucleophilicity. So knowing your nucleophiles from your basic materials is going to help you a lot. So nucleophilicity parallels basicity in the periodic table. If you remember, acidic character increases as we go from left to right, and hence the basic nature or the basic character increases from right to left. It is just the opposite of acidity. Nucleophilicity is also following the same trend. However, when you go down, we will see a little bit of that difference. O negative and S negative. As you go down, the acidity increases. And so when you go up, the basicity increases. But nucleophilicity increases as you go down. Remember, it is all about the polarization and size of the atom. So you have to think about that. Nucleophile wants to move fast. Basic molecule wants to take its own good time, and it would like to have bulk on it. All nucleophiles are Lewis bases. Now remember, what are Lewis bases? Lewis bases are electron donors. So all of the materials that can donate electrons, from example, this C negative and this C negative right here, very important nucleophiles for our course. Okay, so both of them can donate electrons, and hence it will be considered as a great nucleophile despite the bulk on them. So basic molecules go and abstract out the acidic site, whereas a nucleophile will go and attack a electrophilic site. So nucleophile is electron rich, electrophile is electron poor. Most of the times it will be a carbon which will be the electrophile. Okay. So between strong and weak nucleophiles, just remember, weak like water and ammonia, all of those neutral molecules will be our weak nucleophiles. Among the strong nucleophiles, all of our anions except for fluoride will be a strong nucleophile. Remember, the basicity and nucleophilicity will increase from right to left. What is in the right? Fluorine. What is in the left? Carbon. So this is considered as a weak kind of a nucleophile. Large polarizable anions are best. For example, S negative. S is a big atom and can be polarized. Neutral molecules of S, phosphorus or nitrogen molecules are also considered as comparatively strong. Not strong, but maybe moderate. So if you go back to our chart up here, you will see that neutral nitrogen molecules are still considered moderate. Why? Remember, electron donating ability is more in less electronegative elements than more electronegative elements. The more electronegative elements wants to hold on to their electrons, whereas less electronegative elements can still give away electrons compared to more electronegative elements. Even they don't want to, but compared to oxygen, nitrogen will be a stronger electron donor. Okay. So with this knowledge of our nucleophiles and who makes a better nucleophile and what makes a poor nucleophile, we come to the second mechanistic step of our ionic reactions, which are nucleophilic attacks. Now, nucleophilic attacks can be done by two methods. By a negatively charged nucleophile. So remember, there's a negatively charged nucleophiles, which are the strong nucleophiles, and then we have a weak nucleophile, which is neutral nucleophiles. So what happens in a nucleophilic attack? Let's see. CH3, triple bonded C, negative, Na. Now, even if I don't draw my negative and a positive, I want you to remember the metal ion effect. Plus CH3, CH2, CH, positive CH3. Now, before you make this hydrogen acidic kind of a hydrogen, I want to remind you, this carbon has how many bonds? 1, 2, 3. This carbon is very electron poor. And so this carbon is our electrophilic site. And this carbon with extra electrons on it is our nucleophilic site. So just like in your acid-base reactions, you had to find your electron-rich, electron-poor site. In a nucleophilic attack also, you will find your nucleophilic electron-rich site and your electron-poor electrophilic site. And just like in your curved arrow, electron rich attacks the electron poor. You will attack the electron rich to this electron poor carbon. And I'm going to draw my product. I will write all of these 3 carbons right here. CH3, C triple bond C. And what else do I need to make? I need to attach this carbon, A, B, C. So A, B, C. CH3, CH2, CH. And on this, I also have a CH3. Do you see how I made my product? Both of these got added up. So instead of thinking that I'm going to get 2 different products, I got a complex kind of a thing, or a addendum. This is my nucleophilic attack. Also, from 3 carbons here and 4 carbons here, I now have a 1, 2, 3, 4, 5, 6-membered long chain. So this is a very good nucleophilic attack for adding on carbons. Let's look at another example. Why don't all of you draw this in your notebooks also? So I still have a question. Is this reaction going to do acid-base, or is this reaction going to do a nucleophilic attack? So always check that in sequence. First, look out for your acid-base reactions. 9 out of 10 reactions will undergo acid-base reaction. So always check for your acid-base reaction first. Let's try to look at the electron-rich site. So this, among all of these, this is definitely going to be my electron-rich site. Let me see if I can find my acidic hydrogen here. Are my sp3 hydrogen acidic? Is this sp3 hydrogen acidic? It's not. And so we are clear that this reaction is not going to go through an acid-base reaction. We can look forward for a nucleophilic, electrophilic kind of a reaction. Now I know that this is going to be my nucleophile, but where is my electrophile going to be? Anybody? Anyone? Hannah, you want to take a guess? Okay. So to find my electrophile, I'm going to first find a vulnerable site. What is electrophile? An electron poor species. And it usually will be a carbon. So looking at all of these carbons, who has electron deficiency on it? These two sp3s. I'm sorry?
It's the C in the middle.
Exactly. And why?
Because there's a dipole pull towards the Br, making it.
Yes.
Yeah.
Very good, Nelson. This carbon is experiencing an electron pull from this electronegative bromine atom, bringing a partial negative charge here and a partial positive charge here. So this is not a formal positive charge, this is just a partial charge, but nonetheless, it is enough to make this carbon as my electrophilic site. So knowing your nucleophilic site and your electrophilic site is also very important. So what am I going to do? I'm going to do my regular attack. Now remember, carbon cannot accommodate 5 bonds. This carbon already has its 4 bonds. And so if you remember resonance, during resonance, I had told you that you cannot break a single bond. But this is the time that I'm telling you, because 2 different molecules are involved. So within the resonance, when we are doing resonance within the same structure, electrons are moving, you cannot break the single bond. But when 2 different structures are reacting, that is the time that we can kick out the single bond. Everybody seeing what I'm doing? I attacked from electron rich to electron poor, and this CBr bond is now broken. How will I write this out? I will first write my CH3S, followed by this carbon. What does this carbon has? It is A, B, C. So this is my carbon B. Carbon A, carbon C. Carbon A has all the CH3s, carbon C has all the CH3s, carbon B has its hydrogen. So if you remember the first class we came in, and I told you that we will have to remember carbon has only 4 bonds. You have to remember and always check back on that. Plus a Br negative. So this is when you have a negative nucleophile. Either your nucleophile will go ahead and add to a completely formal charged carbon as identified as a nucleophile, or there might be a chance that you have a vulnerable dipole here, which your negative nucleophile can attack and kick out a group, just like we kicked out a group from here. But overall, in both of these cases, what is happening? A nucleophile is attacking a substrate. This is your substrate where the electrophilic site is, and replaces some other moiety. So this is your negatively charged nucleophile. The second nucleophilic attack that we see will be with a neutral protic molecule. Who can tell me what does a protic molecule mean? Anybody? Armani, do you want to give it a shot? A protic material, we looked at it in our module 3. Okay. Anybody else wants to try it?
It's an acid.
A protic material is something that will give away a proton. So usually with an electronegative element, you have a hydrogen that can be given away. Those are known as protic molecules. For example, OH or NH. These hydrogens, which can make hydrogen bonds with other molecules, those are known as protic materials. They can give away a hydrogen. They can hydrogen bond with other molecules. For example, water. For example, alcohols. For example, ammonia. For example, amines, ethylamine, let's say. And so let's do one example here, CH3, CH2, NH2. And I have similar substrate, which I used earlier. So remember, I have this substrate. In this particular case, Your lone pair is going to act as your nucleophilic site. First of all, can I have any acid-base reactions? There are no acidic reactions. The only electron donor is right here. So this will become my base. And if I consider this as my acid, do I have any acidic hydrogens? I do not. So there is no acid-base reaction that is going to be possible for this. Next is substitutions. Yes, this is the electron donor. I will label it as my electrophile, and hence this carbon will be treated as my electrophilic carbon. I will now show my nucleophilic attack. And what do I get? I will get CH3, CH2, CH, CH3. Now, I want you to see, instead of starting from here, I have now started from here. And you can do any of these as long as you have all the carbons, all the other atoms, all the groups from both the structures in the right place. So that is also a possibility that I want you to see. The next is this nitrogen. With how many hydrogens? 2 hydrogens. And what else is attached to this nitrogen? The CH2, CH3. Is this molecule neutral? Remember, overall, this step will generate a positively charged element. And this is in difference to what we saw here. Why? Because we had started out with a negatively charged group. When we attacked on the similar substrate, we just generated our product. We did not generate any intermediate. This is an intermediate that we can isolate, we can separate out. But this is something that will not be allowed to do. Why? Because you don't want to use a positively charged molecule with chloride, with bromide, or any other material. You just want a plain amine. At that point, we will be doing 1, 2, 3 are deprotonations. So don't forget, we have already looked at deprotonation. An external base can be used to remove the hydrogen to get back your neutral product. And this is a step you cannot just skip. So only this part is your nucleophilic attack. We are now dealing with deprotonation. Base attacks one of the hydrogens. Hydrogens break the bond. And why do I say that you need a protic material only? Because if this hydrogen is not present to be removed by the base, your positively charged material will never become neutral. So this is your nucleophilic attack, and you need the deprotonation part to get to your neutral molecule. Okay, so let's look at another example of a neutral molecule. Let's say that we have CH3OH. Remember the protic part here. Now I'm going to use the same substrate that we used earlier. Larion, are you here? Larion Clausel? Are you here? Okay. Larion, do you know, out of these two, will there be a acid-base reaction? Can you guess? So for an acid-base reaction, what is the first thing that we look at? We look at an electron donor. Where is the electron donor present?
On the left.
I'm sorry, could you speak a little? Yeah.
The oxygen.
Excuse me, yes. Yes, it is the oxygen. Very good. The lone pairs of oxygens. So if we consider this to be our base, and this has to be our acid, right? Do you see a acidic hydrogen on this molecule?
No.
No. And so, can we do acid base? No, we cannot. We will have to do the nucleophilic electrophilic attack, right? Where is the electrophile? I'm giving you a hint. The oxygen is the electron donor, and hence we are going to consider it as our nucleophile. But where is our electrophilic site? And this is the electrophile, right? But you have to find that site, which is electrophilic.
It's a bromine.
Okay, the bromine is going to be electron rich because it is electronegative. So where is the electrophilic or the electron poor site, Arian? Just give it a shot. I mean, it may not be right. So far you have been right for everything that you have been saying. But I just want you to tell me which atom will I attack on? Which is the most electron poor site? Which is the most electron poor atom in this molecule? Bromine will not be electron poor because it is electronegative. It is actually pulling electrons towards it, making it a negative, partial negative. You see this part, Larian?
Yeah.
And don't feel bad, right? Nobody else even volunteered. So probably none of them also know this. Or maybe they know this, they don't want to share their information with us. But just take a guess. What about this carbon, Larian? What do you think will be on this carbon? Will it have electrons, normal electrons, or will it have more electrons, or will it have less electrons because of the presence of this bromine?
Less.
Very good. Because it has less electrons than bromine, we say that this carbon is the electrophilic site. Okay, do you understand this, Larian?
Yeah.
Very good. And thank you so much for taking the stab for it on behalf of everyone else. So this carbon is my electrophilic site. My electron rich will attack. This carbon already has 4 bonds, 1, 2, 3, 4. And so it will have to kick out this bromine, just like it did in our previous setup. So remember, in this setup also, the negatively charged attacked it, the bromine left building or the molecule, and this is the structure that we were left with, right? But in this particular case, I have the oxygen, I have the H, and I have the CH3. And I will also have a positive charge on this. Why? Because oxygen can only have 2 bonds. But right now, my nucleophilic addendum has 3 bonds on this oxygen. So up to this part was the nucleophilic attack. Up to this part was the nucleophilic attack. What will come next is the deprotonation. I have my base. The base will go collect this hydrogen. This hydrogen bond will break and a neutral molecule will be generated. So remember, this comes from here, and this O, CH3, comes from here. Do you see this? You need to have a neutral molecule. So from neutral protic materials, you will be generating a positively charged intermediate. You will be doing deprotonations to get your neutral molecule. So any questions so far? This brings us to our third arrow pushing mechanistic step, which is the loss of leaving group. And among all of these, you have already seen the leaving group leave. But how will you know which leaving group will leave? Especially the ones that leave on their own. Okay, and this is where you can look at our leaving group guide. Just like in your acid base, you need a very stable leaving group, right? If you have a reactive leaving group, it will not leave. So the more stable the leaving group is, the better leaving abilities it will have. What is the definition of this part? More stable means weak base. Okay? So if you look at among the halides, the fluorine, chlorine, bromine, iodine, the iodine, which has the biggest of the sizes and the most weak base among all of these four halogens, is considered as the best leaving group. Fluoride, on the other hand, which is a very small atom and the spread of electrons cannot happen here, is considered as a strong base. Well, not a strong base also, but it does not want to give away its electrons. So we don't consider it as strong, we just consider it as reactive, unstable, and reactive. So among the halides, iodine, bromide, and chloride, they have the best leaving abilities. We don't consider fluoride to be a leaving group. Just because you want that whenever your leaving group leaves, for example, in our examples that I have shown you, we were kicking out bromide, right? We kicked out bromide here. That's bromide. And in this case also, we kicked out a bromide. In this case also, we kicked out a bromide. And so, if you have a stable group that is leaving, that will have the best leaving group abilities. A few exceptions that I want to point out. Hydride, even though it is a very small group, small molecule, it is not a great leaving group. Hydride is always considered as a strong base. Sodium hydride. Very, very important. Hydride, even though it's small in size, is not considered as a nucleophile. It is a great leaving group. And so, if you want to make a product with hydride, it is not going to happen. Why? Because hydride is a strong base. What do you need as a leaving group? You need a weak base to be your molecule here. Similarly, if you have sodium hydroxide and you make a product, can you make hydroxide as a leaving group? You cannot. Why? Because this is also a very strong base. So hydrides, hydroxides are bad leaving groups. C negative cannot be a strong base. You cannot break a C-C bond and think that a product and a C negative something will form. Not by breaking a C single bond C, never. We do have C negative charges, but with a element, with a metal ion, sodium ion, and so on. These are our two favorites, C negative molecules. Even this, potassium cyanide and hydrogen cyanide, both of them are sources of cyanide. This is a stronger electron donor. This would be a weaker electron donor. But we are talking about the leaving groups. So just know that hydride, hydroxide, and C negative, you will never have them as your leaving groups. What are other great leaving groups? So water, a complete neutral water, completely neutral alcohols, iodide, bromide, ammonia, neutral ammonia, carboxylic acids. So remember, all of these are neutral. And then sulfonates. Sulfonates are great leaving groups. Why? Because when they will be formed, you will see resonance and induction stabilization, which means stability is very high. High stability means weak reactivity or weak basicity. And so they will be very, very, very weak bases. So triflate, tosylates, and other alkyl sulfonates. Commonly, we call these as OTF. And this is known as a OTS. There is a mesylate also. A mesylate as a methyl group here, which is known as a OMS. So for your course, you need to know where are your great leaving groups and which are your bad leaving groups. So all the halides and all the sulfonates, you have to memorize these. You don't need to know the exact structures for the sulfates, but you must know how we are naming them, or just like this is a triflate, OTF. I will just write OTF, or I might write just OMS, and you must be able to recognize that these have sulfonates in them. Any questions so far? So leaving groups, sometimes we will see, and we will see this in an upcoming mechanism, they can leave on their own. So why this? This is a polar group with this carbon, partial negative, partial positive. The bond breaks and we show the leaving group leave. So what is left behind? This carbon with a positive charge plus a bromide. So when we look at this equation, this is a weak base and hence a great leaving group. Okay, so it could be just an atom or a group of atoms also. But there are two things that you have to fulfill. They have to be a weak base and they should be able to exist independently, or when a nucleophile kicks them out. So for example, we have been looking at it when you have a nucleophile and you have hydrogen, let's say this is CH3, and let's make an iodide here. Now your nucleophile, the electron rich, kicks this carbon. Why this carbon? This carbon is feeling electron poor because of this iodide. This iodide gets the partial negative. This carbon gets the partial positive. So the nucleophile attacks the carbon, and this carbon iodide bond gets kicked up. What is it that you form now? Instead of a positive charge, so I have a CH3 here, CH2 here, and my incoming nucleophile pair, plus my iodide. Again, this is a weak base, very, very weak base, and hence a great leaving group. So these are the two steps that can occur. With leaving groups, we just discussed OH to be a bad leaving group. So there are two methods by which we can make hydroxides great leaving groups. The first is by making water out of OH, and the second is by making a sulfonate out of that water. So let me show you the sulfonate part first. Look at this. There is R. What is R? It could be any alkyl chain. Okay, and I have this OH, and I have this triflate, TFCl. So all of this part is my TF part, the triflate part, and I have the chloride next to it. So I will just label it as TFCl. On your drill test, you can also put it like TFCl. The base, pyridine. Very important combination for these two. And I'll tell you why. This triflate will go attach itself on the oxygen. So this is my oxygen and this is my triflate. So what have I created? I have created my OTF. But what has happened to this hydrogen and this chlorine? Both of these together make HCl. Now, HCl may interfere and cause other acid-base reactions, which we don't want. This is where your pyridine, the mild base will neutralize this HCl. And so whenever you will do a triflate formation, you will always write the triflate or the mesylate or the tosylate with a pyridinium ion. So let's say that you have a group like this, and I have OH. This OH, I'm going to write mesyl chloride or mesylate chloride with pyridine. What am I going to do? I'm going to keep the stereochemistry of this hydrogen intact. This chlorine and this hydrogen are going to make HCl. My pyridine is going to neutralize this HCl and they will be gone out of the system. What is left is this oxygen and this MS. OMS. Now I have a great leaving group. When I will have my nucleophile now, and let's say that I have CN, let's say potassium cyanide. Potassium cyanide, cyanides, C will have the negative charge, potassium will have the positive charge. No acid-base reaction possible here. I only will have a substitution reaction, or a nucleophilic attack will occur at this carbon. Why? Because this is my electrophilic carbon. OMS, CO bond. Still oxygen is pulling the electrons away from this carbon, making this oxygen electron rich, making this carbon electron poor. So this cyanide or the nucleophile will attack my electrophilic carbon right here. This carbon, I already have 4 bonds. I did not draw my 4th hydrogen bond here, but it is there. So this carbon already has 4 bonds. And so this OMS can now be kicked out. What will be my major or more important product be? This particular molecule right here. What about my non-major molecule? What is the rest of the thing left? O and OMS. If you look at this particular chemical reaction, I placed my nucleophile on the arrow, and that is something that you can expect. Instead of me writing A plus B kind of a notation, I have A goes to something using something kind of a notation here. So this is the part where your leaving group was introduced. This is the part when your leaving group leaves. And your leaving group is resonance and induction stabilized. So this is a very, very, very stable group, very weak group also. Another thing that we could have done, we have a OH, we introduce acid. So remember, what is this? H2O plus H, or any acid that I have, this oxygen will go and do an acid-base reaction to generate H3O positive plus the HSO4 negative conjugate base. This is something that we have already done in our module 3. So this hydronium ion is going to be a source of a hydrogen. So let me write it out like this. And remember, I'm writing it again on the arrow, which means I want these two to react. Instead of doing any leaving group, instead of doing any nucleophilic attacks, this reaction is first of all going to do a acid-base reaction. So we want to convert this OH into a great leaving group, but we will do it after this acid-base reaction. So this oxygen is going to act as our basic site. This hydrogen, or any of these hydrogen for that matter of fact, is going to be our acidic site. My base will go and abstract out a hydrogen, kick out this bond, and this acid-base complex will form. So what have we done here? We have repeated the first mechanistic step of protonation. Okay, this is not the leaving group part, this is the protonation part. Now, because the leaving groups can leave on their own. So remember, some of the leaving groups can leave on their own. This is what this is going to do. The leaving group leaves on its own. And how do you know that this leaving group can exist on its own? Because water is a weak base and it can exist independently also. Meanwhile, what will happen to the rest of this molecule right here? This carbon has a H, right? It already had that H. But now How many bonds this carbon has? It has lost one of its 4 bonds, and we have generated
Positive.
a positive charge. Very good. This is a carbocation. So with the OH, you can either introduce a mesylate or a tosylate or a triflate chloride to generate a good leaving group, or you can introduce a acidic medium to generate a good leaving group. So here also you had generated a good leaving group as OMS. Here also you have generated a good leaving group as water. So make sure that you practice these mechanisms before you come to class tomorrow, because we are going to pick up from the carbocation, which will be our 4th mechanistic arrow. Okay, very good.